search or breadth first search in the context of solving a maze, for example. So I'll go ahead and go into my terminal. And what I have here inside of maze.py is an implementation of this same idea of maze solving. I've defined a class called node that in this case is keeping track of the state, the parent, in other words, the state before the state, and the action. In this case, we're not keeping track of the path cost because we can calculate the cost of the path at the end after we found our way from the initial state to the goal. In addition to this, I've defined a class called a stack frontier. And if unfamiliar with a class is a way for me to define a way to generate objects in Python. It refers to an idea of object-oriented programming, where the idea here is that I would like to create an object that is able to store all of my frontier data, and I would like to have functions, otherwise known as methods, on that object that I can use to manipulate the object. And so what's going on here, if unfamiliar with the syntax, is I have a function that initially creates a frontier that I'm going to represent using a list. And initially, my frontier is represented by the empty list. There's nothing in my frontier to begin with. I have an add function that adds something to the frontier, as by appending it to the end of the list. I have a function that checks if the frontier contains a particular state. I have an empty function that checks if the frontier is empty. If the frontier is empty, that just means the length of the frontier is 0. And then I have a function for removing something from the frontier. I can't remove something from the frontier if the frontier is empty, so I check for that first. But otherwise, if the frontier isn't empty, recall that I'm implementing this frontier as a stack, a last in, first out data structure, which means the last thing I add to the frontier, in other words, the last thing in the list, is the item that I should remove from this frontier. So what you'll see here is I have removed the last item of a list. And if you index into a Python list with -1, that gets you the last item in the list. Since 0 is the first item, -1 kind of wraps around and gets you to the last item in the list. So we give that the node. We call that node. We update the frontier here on line 28 to say, go ahead and remove that node that you just removed from the frontier. And then we return the node as a result. So this class here effectively implements the idea of a frontier. It gives me a way to add something to a frontier and a way to remove something from the frontier as a stack. I've also, just for good measure, implemented an alternative version of the same thing called a queue frontier, which, in parentheses, you'll see here, it inherits from a stack frontier, meaning it's going to do all the same things that the stack frontier did, except the way we remove a node from the frontier is going to be slightly different. Instead of removing from the end of the list, the way we would in a stack, we're instead going to remove from the beginning of the list. Self.frontier0 will get me the first node in the frontier, the first one that was added, and that is going to be the one that we return in the case of a queue. Then under here, I have a definition of a class called maze. This is going to handle the process of taking a sequence, a maze-like text file, and figuring out how to solve it. So it will take as input a text file that looks something like this, for example, where we see hash marks that are here representing walls, and I have the character A representing the starting position, and the character B representing the ending position. And you can take a look at the code for parsing this text file right now. That's the less interesting part. The more interesting part is this solve function here, where the solve function is going to figure out how to actually get from point A to point B. And here we see an implementation of the exact same idea we saw from a moment ago. We're going to keep track of how many states we've explored, just so we can report that data later. But I start with a node that represents just the start state. And I start with a frontier that in this case is a stack frontier. And given that I'm treating my frontier as a stack, you might imagine that the algorithm I'm using here is now depth first search, because depth first search, or DFS, uses a stack as its data structure. And initially, this frontier is just going to contain the start state. We initialize an explored set that initially is empty. There's nothing we've explored so far. And now here's our loop, that notion of repeating something again and again. First, we check if the frontier is empty by calling that empty function that we saw the implementation of a moment ago. And if the frontier is indeed empty, we'll go ahead and raise an exception, or a Python error, to say, sorry, there is no solution to this problem. Otherwise, we'll go ahead and remove a node from the frontier, as by calling frontier.remove, and update the number of states we've explored, because now we've explored one additional state. So we say self.numExplored plus equals 1, adding 1 to the number of states we've explored. Once we remove a node from the frontier, recall that the next step is to see whether or not it's the goal test. And in the case of the maze, the goal is pretty easy. I check to see whether the state of the node is equal to the goal. Initially, when I set up the maze, I set up this value called goal, which is a property of the maze, so I can just check to see if the node is actually the goal. And if it is the goal, then what I want to do is backtrack my way towards figuring out what actions I took in order to get to this goal. And how do I do that? Well, recall that every node stores its parent, the node that came before it that we used to get to this node, and also the action used in order to get there. So I can create this loop where I'm constantly just looking at the parent of every node and keeping track for all of the parents what action I took to get from the parent to this current node. So this loop is going to keep repeating this process of looking through all of the parent nodes until we get back to the initial state, which has no parent, where node.parent is going to be equal to none. As I do so, I'm going to be building up the list of all of the actions that I'm following and the list of all of the cells that are part of this solution. But I'll reverse them because when I build it up, going from the goal back to the initial state, I'm building the sequence of actions from the goal to the initial state, but I want to reverse them in order to get the sequence of actions from the initial state to the goal. And that is ultimately going to be the solution. So all of that happens if the current state is equal to the goal. And otherwise, if it's not the goal, well, then I'll go ahead and add this state to the explored set to say, I've explored this state now. No need to go back to it if I come across it in the future. And then this logic here implements the idea of adding neighbors to the frontier. I'm saying, look at all of my neighbors, and I implemented a function called neighbors that you can take a look at. And for each of those neighbors, I'm going to check, is the state already in the frontier? Is the state already in the explored set? And if it's not in either of those, then I'll go ahead and add this new child node, this new node, to the frontier. So there's a fair amount of syntax here, but the key here is not to understand all the nuances of the syntax, so feel free to take a closer look at this file on your own to get a sense for how it is working. But the key is to see how this is an implementation of the same pseudocode, the same idea that we were describing a moment ago on the screen when we were looking at the steps that we might follow in order to solve this kind of search problem. So now let's actually see this in action. I'll go ahead and run maze.py on maze1.txt, for example. And what we'll see is here we have a printout of what the maze initially looked like. And then here down below is after we've solved it. We had to explore 11 states in order to do it, and we found a path from A to B. And in this program, I just happened to generate a graphical representation of this as well. So I can open up maze.png, which is generated by this program, that shows you where in the darker color here are the walls, red is the initial state, green is the goal, and yellow is the path that was followed. We found a path from the initial state to the goal. But now let's take a look at a more sophisticated maze to see what might happen instead. Let's look now at maze2.txt. Where now here, we have a much larger maze. Again, we're trying to find our way from point A to point B. But now you'll imagine that depth first search might not be so lucky. It might not get the goal on the first try. It might have to follow one path, then backtrack and explore something else a little bit later. So let's try this. We'll run python maze.py of maze2.txt, this time trying on this other maze. And now, depth first search is able to find a solution. Here, as indicated by the stars, is a way to get from A to B. And we can represent this visually by opening up this maze. Here's what that maze looks like. And highlighted in yellow is the path that was found from the initial state to the goal. But how many states did we have to explore before we found that path? Well, recall that in my program, I was keeping track of the number of states that we've explored so far. And so I can go back to the terminal and see that, all right, in order to solve this problem, we had to explore 399 different states. And in fact, if I make one small modification to the program and tell the program at the end when we output this image, I added an argument called showExplored. And if I set showExplored equal to true and rerun this program, python maze.py, running it on maze2, and then I open the maze, what you'll see here is highlighted in red are all of the states that had to be explored to get from the initial state to the goal. Depth first search, or DFS, didn't find its way to the goal right away. It made a choice to first explore this direction. And when it explored this direction, it had to follow every conceivable path all the way to the very end, even this long and winding one, in order to realize that, you know what? that's a dead end. And instead, the program needed to backtrack. After going this direction, it must have gone this direction. It got lucky here by just not choosing this path. But it got unlucky here, exploring this direction, exploring a bunch of states it didn't need to, and then likewise exploring all of this top part of the graph when it probably didn't need to do that either. So all in all, depth-first search here really not performing optimally, or probably exploring more states than it needs to. It finds an optimal solution, the best path to the goal, but the number of states needed to explore in order to do so, the number of steps I had to take, that was much higher. So let's compare. How would breadth-first search, or BFS, do on this exact same maze instead? And in order to do so, it's a very easy change. The algorithm for DFS and BFS is identical, with the exception of what data structure we use to represent the frontier. That in DFS, I used a stack frontier, last in, first out, whereas in BFS, I'm going to use a queue frontier, first in, first out, where the first thing I add to the frontier is the first thing that I remove. So I'll go back to the terminal, rerun this program on the same maze, and now you'll see that the number of states we had to explore was only 77, as compared to almost 400 when we used depth-first search. And we can see exactly why. We can see what happened if we open up maze.png now and take a look. Again, yellow highlight is the solution that breadth-first search found, which incidentally is the same solution that depth-first search found. They're both finding the best solution, but notice all the white unexplored cells. There was much fewer states that needed to be explored in order to make our way to the goal, because breadth-first search operates a little more shallowly. It's exploring things that are close to the initial state without exploring things that are further away. So if the goal is not too far away, then breadth-first search can actually behave quite effectively on a maze that looks a little something like this. Now, in this case, both BFS and DFS ended up finding the same solution, but that won't always be the case. And in fact, let's take a look at one more example. For instance, maze3.txt. In maze3.txt, notice that here there are multiple ways that you could get from A to B. It's a relatively small maze, but let's look at what happens. If I use, and I'll go ahead and turn off show explored, so we just see the solution. If I use BFS, breadth-first search, to solve maze3.txt, well, then we find a solution. And if I open up the maze, here's the solution that we found. It is the optimal one. With just 4 steps, we can get from the initial state to what the goal happens to be. But what happens if we tried to use depth-first search, or DFS, instead? Well, again, I'll go back up to my queue frontier, where queue frontier means that we're using breadth-first search. And I'll change it to a stack frontier, which means that now we'll be using depth-first search. I'll rerun python maze.py. And now you'll see that we find a solution, but it is not the optimal solution. This, instead, is what our algorithm finds. And maybe depth-first search would have found the solution. It's possible, but it's not guaranteed. That if we just happen to be unlucky, if we choose this state instead of that state, then depth-first search might find a longer route to get from the initial state to the goal. So we do see some trade-offs here, where depth-first search might not find the optimal solution. So at that point, it seems like breadth-first search is pretty good. Is that the best we can do, where it's going to find us the optimal solution, and we don't have to worry about situations where we might end up finding a longer path to the solution than what actually exists, where the goal is far away from the initial state, and we might have to take lots of steps in order to get from the initial state to the goal. What ended up happening is that this algorithm, BFS, ended up exploring basically the entire graph, having to go through the entire maze in order to find its way from the initial state to the goal state. What we'd ultimately like is for our algorithm to be a little bit more intelligent. And now what would it mean for our algorithm to be a little bit more intelligent in this case? Well, let's look back to where breadth-first search might have been able to make a different decision and consider human intuition in this process as well. Like, what might a human do when solving this maze that is different than what BFS ultimately chose to do? Well, the very first decision point that BFS made was right here, when it made 5 steps and ended up in a position where it had a fork in the road. It could either go left or it could go right. In these initial couple steps, there was no choice. There was only one action that could be taken from each of those states. And so the search algorithm did the only thing that any search algorithm could do, which is keep following that state after the next state. But this decision point is where things get a little bit interesting. Depth-first search, that very first search algorithm we looked at, chose to say, let's pick one path and exhaust that path. See if anything that way has the goal. And if not, then let's try the other way. Breadth-first search took the alternative approach of saying, you know what, let's explore things that are shallow, close to us first. Look left and right, then back left and back right, so on and so forth, alternating between our options in the hopes of finding something nearby. But ultimately, what might a human do if confronted with a situation like this of go left or go right? Well, a human might visually see that, all right, I'm trying to get to state B, which is way up there, and going right just feels like it's closer to the goal. Like it feels like going right should be better than going left because I'm making progress towards getting to that goal. Now, of course, there are a couple of assumptions that I'm making here. I'm making the assumption that we can represent this grid as like a two-dimensional grid where I know the coordinates of everything. I know that A is in coordinate 0, 0, and B is in some other coordinate pair, and I know what coordinate I'm at now. So I can calculate that, yeah, going this way, that is closer to the goal. And that might be a reasonable assumption for some types of search problems, but maybe not in others. But for now, we'll go ahead and assume that I know what my current coordinate pair is, and I know the coordinate, xy, of the goal that I'm trying to get to. And in this situation, I'd like an algorithm that is a little bit more intelligent, that somehow knows that I should be making progress towards the goal, and this is probably the way to do that, because in a maze, moving in the coordinate direction of the goal is usually, though not always, a good thing. And so here we draw a distinction between two different types of search algorithms, uninformed search and informed search. Uninformed search algorithms are algorithms like DFS and BFS, the two algorithms that we just looked at, which are search strategies that don't use any problem-specific knowledge to be able to solve the problem. DFS and BFS didn't really care about the structure of the maze or anything about the way that a maze is in order to solve the problem. They just look at the actions available and choose from those actions, and it doesn't matter whether it's a maze or some other problem. The solution or the way that it tries to solve the problem is really fundamentally going to be the same. What we're going to take a look at now is an improvement upon uninformed search. We're going to take a look at informed search. Informed search are going to be search strategies that use knowledge specific to the problem to be able to better find a solution. And in the case of a maze, this like problem-specific knowledge is something like, if I'm in a square that is geographically closer to the goal, that is better than being in a square that is geographically further away. And this is something we can only know by thinking about this problem and reasoning about what knowledge might be helpful for our AI agent to know a little something about. There are a number of different types of informed search. Specifically, first, we're going to look at a particular type of search algorithm called greedy best-first search. Greedy best-first search, often abbreviated GBFS, is a search algorithm that instead of expanding the deepest node like DFS or the shallowest node like BFS, this algorithm is always going to expand the node that it thinks is closest to the goal. Now, the search algorithm isn't going to know for sure whether it is the closest thing to the goal. Because if we knew what was closest to the goal all the time, then we would already have a solution. Like the knowledge of what is close to the goal, we could just follow those steps in order to get from the initial position to the solution. But if we don't know the solution, meaning we don't know exactly what's closest to the goal, instead, we can use an estimate of what's closest to the goal, otherwise known as a heuristic, just some way of estimating whether or not we're close to the goal. And we'll do so using a heuristic function, conventionally called h of n, that takes a state as input and returns our estimate of how close we are to the goal. So what might this heuristic function actually look like in the case of a maze-solving algorithm, where we're trying to solve a maze? What does a heuristic look like? Well, the heuristic needs to answer a question like, between these two cells, C and D, which one is better? Which one would I rather be in if I'm trying to find my way to the goal? Well, any human could probably look at this and tell you, you know what, D looks like it's better. Even if the maze is convoluted and you haven't thought about all the walls, D is probably better. And why is D better? Well, because if you ignore the walls, let's just pretend the walls don't exist for a moment and relax the problem, so to speak. D, just in terms of like coordinate pairs, is closer to this goal. It's fewer steps that I would need to take to get to the goal as compared to C, even if you ignore the walls. If you just know the xy coordinate of C and the xy coordinate of the goal, and likewise you know the xy coordinate of D, you can calculate that D, just geographically, ignoring the walls, looks like it's better. And so this is the heuristic function that we're going to use. And it's something called the Manhattan distance, one specific type of heuristic, where the heuristic is how many squares vertically and horizontally, and then left to right, so not allowing myself to go diagonally, just either up or right or left or down. How many steps do I need to take to get from each of these cells to the goal? Well, as it turns out, D is much closer. There are fewer steps. It only needs to take 6 steps in order to get to that goal. Again here, ignoring the walls. We've relaxed the problem a little bit. We're just concerned with, if you do the math to subtract the x values from each other and the y values from each other, what is our estimate of how far we are away? We can estimate that D is closer to the goal than C is. And so now we have an approach. We have a way of picking which node to remove from the frontier. And at each stage in our algorithm, we're going to remove a node from the frontier. We're going to explore the node if it has the smallest value for this heuristic function, if it has the smallest Manhattan distance to the goal. And so what would this actually look like? Well, let me first label this graph, label this maze, with a number representing the value of this heuristic function, the value of the Manhattan distance from any of these cells. So from this cell, for example, we're 1 away from the goal. From this cell, we're 2 away from the goal, 3 away, 4 away. Here, we're 5 away, because we have to go 1 to the right and then 4 up. From somewhere like here, the Manhattan distance is 2. We're only 2 squares away from the goal geographically, even though in practices we're going to have to take a longer path. But we don't know that yet. The heuristic is just some easy way to estimate how far we are away from the goal. And maybe our heuristic is overly optimistic. It thinks that, yeah, we're only 2 steps away, when in practice, when you consider the walls, it might be more steps. So the important thing here is that the heuristic isn't a guarantee of how many steps it's going to take. It is estimating. It's an attempt at trying to approximate. And it does seem generally the case that the squares that look closer to the goal have smaller values for the heuristic function than squares that are further away. So now, using greedy best first search, what might this algorithm actually do? Well, again, for these first 5 steps, there's not much of a choice. We start at this initial state A, and we say, all right, we have to explore these 5 states. But now we have a decision point. Now we have a choice between going left and going right. And before, when DFS and BFS would just pick arbitrarily, because it just depends on the order you throw these 2 nodes into the frontier, and we didn't specify what order you put them into the frontier, only the order you take them out. Here we can look at 13 and 11 and say that, all right, this square is a distance of 11 away from the goal according to our heuristic, according to our estimate. And this one, we estimate to be 13 away from the goal. So between those 2 options, between these 2 choices, I'd rather have the 11. I'd rather be 11 steps away from the goal, so I'll go to the right. We're able to make an informed decision because we know a little something more about this problem. So then we keep following, 10, 9, 8. Between the 2 7s, we don't really have much of a way to know between those, so then we do just have to make an arbitrary choice. And you know what? Maybe we choose wrong. But that's OK, because now we can still say, all right, let's try this 7. We say 7, 6. We have to make this choice, even though it increases the value of the heuristic function. But now we have another decision point between 6 and 8. And between those 2, and really we're also considering this 13, but that's much higher. Between 6, 8, and 13, well, the 6 is the smallest value, so we'd rather take the 6. We're able to make an informed decision that going this way to the right is probably better than going down. So we turn this way, we go to 5. And now we find a decision point where we'll actually make a decision that we might not want to make, but there's unfortunately not too much of a way around this. We see 4 and 6. 4 looks closer to the goal, right? It's going up, and the goal is further up. So we end up taking that route, which ultimately leads us to a dead end. But that's OK, because we can still say, all right, now let's try the 6. And now follow this route that will ultimately lead us to the goal. And so this now is how greedy best first search might try to approach this problem, by saying whenever we have a decision between multiple nodes that we could explore, let's explore the node that has the smallest value of h of n, this heuristic function that is estimating how far I have to go. And it just so happens that in this case, we end up doing better in terms of the number of states we needed to explore than BFS needed to. BFS explored all of this section and all of that section, but we were able to eliminate that by taking advantage of this heuristic, this knowledge about how close we are to the goal, or some estimate of that idea. So this seems much better. So wouldn't we always prefer an algorithm like this over an algorithm like breadth first search? Well, maybe. One thing to take into consideration is that we need to come up with a good heuristic. How good the heuristic is going to affect how good this algorithm is. And coming up with a good heuristic can oftentimes be challenging. But the other thing to consider is to ask the question, just as we did with the prior two algorithms, is this algorithm optimal? Will it always find the shortest path from the initial state to the goal? And to answer that question, let's take a look at this example for a moment. Take a look at this example. Again, we're trying to get from A to B. And again, I've labeled each of the cells with their Manhattan distance from the goal, the number of squares up and to the right you would need to travel in order to get from that square to the goal. And let's think about, would greedy best first search that always picks the smallest number end up finding the optimal solution? So what is the shortest solution, and would this algorithm find it? And the important thing to realize is that right here is the decision point. We're estimated to be 12 away from the goal, and we have two choices. We can go to the left, which we estimate to be 13 away from the goal, or we can go up, where we estimate it to be 11 away from the goal. And between those two, greedy best first search is going to say the 11 looks better than the 13. And in doing so, greedy best first search will end up finding this path to the goal. But it turns out this path is not optimal. There is a way to get to the goal using fewer steps, and it's actually this way that ultimately involved fewer steps, even though it meant at this moment choosing the worst option between the two, or what we estimated to be the worst option based on the heuristics. And so this is what we mean by this is a greedy algorithm. It's making the best decision locally. At this decision point, it looks like it's better to go here than it is to go to the 13. But in the big picture, it's not necessarily optimal, that it might find a solution when in actuality there was a better solution available. So we would like some way to solve this problem. We like the idea of this heuristic, of being able to estimate the path, the distance between us and the goal. And that helps us to be able to make better decisions and to eliminate having to search through entire parts of this state space. But we would like to modify the algorithm so that we can achieve optimality, so that it can be optimal. And what is the way to do this? What is the intuition here? Well, let's take a look at this problem. In this initial problem, greedy best first search found us this solution here, this long path. And the reason why it wasn't great is because, yes, the heuristic numbers went down pretty low, but later on, they started to build back up. They built back 8, 9, 10, 11, all the way up to 12 in this case. And so how might we go about trying to improve this algorithm? Well, one thing that we might realize is that if we go all the way through this algorithm, through this path, and we end up going to the 12, and we've had to take this many steps, like who knows how many steps that is, just to get to this 12, we could have also, as an alternative, taken much fewer steps, just 6 steps, and ended up at this 13 here. And yes, 13 is more than 12, so it looks like it's not as good, but it required far fewer steps. Right? It only took 6 steps to get to this 13 versus many more steps to get to this 12. And while greedy best first search says, oh, well, 12 is better than 13, so pick the 12, we might more intelligently say, I'd rather be somewhere that heuristically looks like it takes slightly longer if I can get there much more quickly. And we're going to encode that